Fine.
Yeah. Right.
Okay, the next talk is tidal deformation and dissipation of a rotating black hole by Horng, Sheng, Chia. Please go ahead.
All right. Hi, everyone. My name is Horng Sheng. Thank you to the organizers for having me. It's a pleasure to be able to speak on this occasion. First of all, I have to apologize that I wasn't aware of this workshop before registration closed, so I wasn't able to fully participate in the workshop and the conference. But I've been watching some of the videos online, so have a rough sense of what has been discussed. But I hope that my talk, I'm not over repeating things that that sort of like well discussed already in the workshop. Now, as the title of the talk suggests, today I want to talk about how black holes, or more generally rotating black holes, would respond to the perturbations that's sourced by an external tidal field. And just as an obligatory introduction slide, and I think everyone in the audience would agree that we really are living in a golden era of observational black hole astronomy. So the LIGO and Virgo detectors have detected about 50 binary black holes. And this number is expected to increase very rapidly in the near future. So, there are many more black holes that we can observe. And given the plurality of the signals, you can ask, what type of physics can you learn from these signals, specifically about the nature of the binary constituents? Now, if you take a step back and forget about black holes for the moment and just think about having binary coalescences of general compact objects. So at leading order, you would model them as point particles with masses and spins, and would compute, say, post-Newtonian or post-Minkowskian dynamics. But of course, if you want to probe the nature of these binary constituents, you would have to go beyond the point particle approximation. And this is what the so-called finite size effects are for. And at leading order, these finite size effects is captured by the so-called tidal deformability of the object. So this kind of like classic tidal bulge that would be exerted by the tidal forces sourced by a binary companion. And the tidal deformability of that object is quantified by so-called lift numbers, whose values depend sensitively on the internal structure of the body. Now, in addition to tidal deformability, the nature of these compact objects are also described by their viscosity, which essentially tells you how much energy and angular momentum can be transferred from the body with its external tidal environment. So, and this is often called tidal dissipation, but there are many names for the same phenomena. It's often called tidal heating, tidal torquing, tidal acceleration, and so on. All of them, different names for the same phenomenon. For example, in the most well-known example of a two-body problem, the Earth and Moon system, it is known that tidal dissipation leads to the very gradual spin down of Earth, along with the very gradual recession of Moon away from us due to a torque exerted by this viscous effect. Now, both tidal deformation and dissipation leave distinct imprints in the phase of gravitational waveforms. For example, it is well known that the deformability parameter first appears at the 5th post-Newtonian order in the phase of gravitational waveforms. And tidal dissipation of rotating body first appears at 2.5 pn order in the phase of waveforms. So a precise measurement of these tidal effects in waveforms, in principle, would allow us to probe the nature of these binary constituents, of course, in addition to masses and spins. So what sort of physics can you extract from these tidal effects? This is just a summary slide, by no means comprehensive. For example, one of the most important science cases in the LIGO-Virgo collaboration, or gravitational wave science in general, is to measure the tidal deformability parameter of neutron stars, which allow us to probe the nuclear equation of state at the core of these dense stars, which would indirectly allow us to probe the high density and low temperature regime of the QCD phase diagram. And on a more speculative note, a measurement of these tidal effects, which are different from those of black holes and neutron stars, would allow us to provide hints of the presence of new types of compact objects. And there are no short of examples in the literature on what these type of physics beyond the standard model objects could be: superradiant clouds, boson stars, fermion stars, so on and so forth, you name it. But all of this is just to say that this is, I think, a very exciting science case for gravitational wave astronomy as well. So black holes are, they're fascinating, but of course they're also in some sense remarkably simple, because as an observer at asymptotic infinity, we basically just describe black holes by their masses and spins, essentially because of the O'Hare theorem. And of course, like binary black holes are the most abundant sources of gravitational waves that we have observed. So a detailed understanding of these tidal effects of black holes is not only of interest in gravitational astrophysics, but argue that it is also, it could shed light on the fundamental nature of gravity in general. So the upshot of this talk is that there's been recent progress in computing the tidal deformability and tidal dissipation of rotating black holes. And we find that in the presence of a static tidal field, the Love numbers of curved black holes vanish identically. So this fact has actually been known for some time for Schwarzschild black hole, about more than 10 years ago or so. But again, the recent progress has been sort of generalizing that result to arbitrary spinning black holes. And for both electric type, magnetic type, tidal fields, I'll explain that a little bit in more detail. So that's the deformation part of the response. Tidal dissipation of black holes is also fascinating, because for a Schwarzschild black hole, you have this normal intuition that because of the one-way nature, or the one-way membrane nature of the event horizon, energy and angular momentum that falls into a black hole would be permanently lost from the environment, right? This essentially, this gives rise to the viscous nature of a black hole. But very remarkably, and it's well known in the black hole physics literature, that for highly rotating black holes, you can do the opposite. You can actually extract energy and angular momentum from a highly rotating black hole. And this is a phenomenon that's known as black hole superradiance. And so in this work, and recently there's been multiple independent groups that have computed the dissipative response of curved black holes to arbitrary spins as well. So that's the broad big picture of my talk. I hope it gives you a good sense of where I'm heading to. So in the rest of my talk, I'm going to divide the talk into 3 parts. In the first part, I'll provide a brief recap of several things. First of all, it turns out that these deformation and dissipation effects are nothing but gravitational analogs of susceptibilities in ENM. So I think it is instructive that we take a step back and consider susceptibilities in ENM before I move on to talking about these tidal responses in Newtonian gravity. And then at the end of this first part of the talk, I'll talk about black hole perturbation theory, simply because I'm deriving these tidal responses for black holes. I'll briefly describe I'll describe the latter 2 parts of my talk later on. Are there any questions before I move on? Okay, I hope it's clear. Right, so in ENM, so imagine having a blob of material, right? And you apply an external electric field on this material. What would happen is that the dipole moments of the material would just organize themselves and acquire an induced polarization that we call P. And the constant of proportionality between the external electric field and the polarization vector is what is called susceptibility, that called chi E in here. So if you apply E, what you measure ultimately is the sum of E and P. One interesting thing is that in the limit where this external electric field is static, there's no time scale associated to the system, and therefore the material would polarize instantaneously. But of course, in general, the external electric field can vary with time. And therefore, in that case, the material would not polarize instantaneously, but rather it would have a typical delay timescale associated to its response. In general, the response function now would be simply a convolution of the susceptibility coefficient and the external electric field. But in the limit where the external electric field is slowly varying with time, you can perform a systematic time derivative expansion, and you would find that the polarization has the following form, where leading order, you just restore the static response term that I showed you in the slide earlier. But now, because of the time varying electric field, there's a new term here that's E dot, the time derivative acting on the external electric field. And this term corresponds to the dissipative effect of the material. And the easy way of understanding this is associated to dissipation is because this term involves a single power and time derivative, and therefore it is not invariant under time reversal, and so it does not conserve energy. So chi E1 here is simply some dimensionless constant quantifying how efficient you radiate. And tau naught here is the typical delay time scale associated to this dynamical electromagnetic response. So this is the relationship in the time domain. If you do a Fourier transformation, well, of course, a convolution in the time domain, which is simply give me a product of relations in the frequency domain. And in this case, you would have this simple relationship where omega here is the frequency of the external electric field. Now, and this frequency-dependent susceptibility parameter has these two forms at leading order. And the key takeaway from this slide, and in fact, in the entire talk, if not, is that this susceptibility parameter has two components to it, two broad classes to it, one which is the real part, and the other which is the imaginary part in the response function. In particular, the real part of this susceptibility corresponds to the conservative induced polarization of the medium, whereas the imaginary part gives rise to the dissipative effect of the response. So that was E&M in a nutshell. Now, moving on to Newtonian gravity, imagine having a spherical body that's perturbed by an orbiting companion, which sources an external tidal field. Now, in the limit where the external tidal field is static, the induced mass moment of the body is proportional to the external electric tidal field, and the constant of proportionality is what is often called the Love numbers. So non-vanishing Love numbers give rise to these classic sort of tidal bulging of a spherical, unperturbed spherical body. Well, of course, in practice, the binary companion is orbiting around the body, and so the external tidal field is varying with time as well. And again, in the limit where the external tidal field is slowly varying with time, the induced response has the following expression, where again, at leading order, we have the static tides, where K being the Love numbers that I showed you earlier on. And then analogous to E&M, I have a new term here, which is E dot, the time derivative acting on the external tidal field. And this is exactly the tidal dissipation term associated to the object's response. Now, new here is what I call the dissipation numbers, which just quantifies the viscosity of the body. And tau naught here is a typical delay time scale associated to this response. Now, it is well known in the astrophysics literature that this typical delay time scale would lead to a viscosity-induced time lag or phase lag between the direction of the bulge of a body and the location of the binary companion. Similarly, just like in E&M, in Fourier space, the tidal response of this non-rotating body would have this simple form, where F here is what I call the response function of the star, and frequency now, omega now is the frequency of the external tidal field. And crucially, just like in ENM, the real part of the response function corresponds to conservative tidal effects for the Luft numbers, whereas the imaginary part corresponds to the dissipative effect of the response. So this very simple but crucial observation will play an important role in what I'm going to discuss later about the responses of black holes. And I hope this is clear. So that was strictly the tidal response of a rotating body. You can ask what happens for a previously it was a tidal response of a non-rotating body. And you can ask what happens for the response of a rotating body in Newtonian gravity. And in this case, the functional form that I showed you early on applies, except there's a caveat right now, which is that these expressions here, so the L and M, the frequency, etc., they depend on the frame of reference that you are in. Essentially now, because there is you can either be in the co-rotating frame of a body, or you can be in the observer frame of the body, and depending on which you are in, the frequency that's perceived of the external tidal field can change accordingly. And the perceived frequency of external tidal field would be related in this form, where omega here is the angular frequency of the rotating body. And this is sort of qualitatively different from a non-spinning body, because for a spinning object, when you have a strict static external tidal field, you can still experience tidal dissipation. And the intuitive explanation for that is that when you have a strict static tidal field, a rotating body in the co-rotating frame of this system would perceive the static tidal field to be rotating at a frequency that's proportional to its spin. And therefore, because of this relative time difference between the external tidal field and the motion of the body, one can still experience tidal dissipation, even for a static tide. So in ENM, we measure the induced polarization by measuring E plus P. And now in Newtonian gravity, you measure the response of a body by measuring the Newtonian potential, where leading order is just a point particle limit, m over r. And then now, because of the tidal interactions, you can decompose the remaining terms into two parts. One essentially that's often known as the so-called growing term. And this term arises simply because of the tidal field that's sourced by the external environment. But crucially now, there's also the so-called decaying term, whose coefficient is exactly the response function that I showed you earlier on. So one would read off the response of a self-gravitating body by measuring the coefficient of this decaying term. So I was focusing on Newtonian gravity earlier on, and it's well known that in GR, there's actually a new class of tidal field, the so-called magnetic type tidal fields, to which there is no Newtonian analog. And the magnetic type tidal fields are simply sourced by motion of relativistic fast-moving gravitational bodies. So I'm not going to go into details, except just to say that there are these type of tidal responses is exactly analogous to magnetic susceptibilities in ENM. So they're qualitatively similar in both of these cases. Are there any questions before I move on to a brief introduction to black hole perturbation theory? All right, if not, black hole perturbation theory. So it turns out that for various practical reasons, it is convenient that we decompose the Wild tensor into 5 complex Wild scalars through the so-called Newman-Penrose formalism of general relativity. So in 4 dimensions, there are 10 components in the Wild tensor, and so you can decompose them in this formalism, 5 complex Wild scalar fields, which is often called psi 0 up to psi 4. I'm not going to go into the details of these scalar quantities, except I just want to highlight that it has some nice analogies with E&M as well. In particular, it obeys something that's known as the Peeling theorem. So in this paper, the authors have shown that the scalars obey the scaling as r approaches infinity, such that at large distances, it is psi 4 that sort of dominates the gravitational field. And in fact, it is well known in the literature that psi 4 can be simply related to the two polarizations of gravitational waves through these two time derivatives. And of course, this is just analogous to an E&M where you have the near zone, the induction zone, and the far or radiative zone, right? And psi 4 is really the quantity that I will be focusing on in the rest of my talk. So these wild scalars are especially relevant in the context of black hole perturbation theory because of the Tzkowski equation. And I'm sure many in the audience knows that the Tzkowski equation is a very powerful formalism that allows us to decouple the complicated set of PDEs of Einstein's equation into a set of coupled ODEs, assuming that the background spacetime is described by the Kerr geometry. And this method is so powerful that there have been, over the past few decades, there have been many heroic computations of the gravitational wave fluxes emitted from these extreme mass ratio inspirals using the Tzkowski equation. And these flux expressions have been computed to extremely high post-Newtonian orders. I think the last I checked, for Schwarzschild spacetime, people have computed the flux expression up to 22 PN order or something of that order of magnitude. So it's a really impressive high PN calculation that one can pursue. So just a bit of more details into the Tzkowski equation, which is that this psi 4 here obeys this separable ansatz, where v here is a time coordinate, an advanced time coordinate, and phi is just the azimuthal angle. So this part of the ansatz here is simply sort of satisfies the explicit isometry of the curved background spacetime. Of course, the power of the Tzkowski equation is that Tzkowski found that the r and the theta coordinates are also separable through this so-called spin-weighted spheroidal harmonics. So one would ultimately just solve a coupled set of ODE of r and theta as a result of this. Now, one interesting fact that is sort of not very obviously mentioned in the literature, but in this context is especially important, is that there's also a constant, an overall constant here, and the separable ansatz for each value of L and M. And these constants just tell you how strong the modes are in this perturbation. And one can show that the real part of this constant is actually proportional to the electric type tidal field, whereas the imaginary part is proportional to the magnetic type tidal field. And so this is just to emphasize that the Tzkowski equation really captures perturbations of both electric type and magnetic type tides. And this is true for all values of L and M. Of course, the essential assumption of the Tzkowski equation is that you're working with linear perturbations. So it is still working the regime of linear perturbation theory. But apart from that, this relation holds for all values of L and M.
May I ask a question, which is
sure
quite naive? Can't you absorb this MLM into RRS? Is there any normalization condition on RNS?
Sorry, what is RS?
The one that appear in RLM and
RLM. Sorry, yes.
Can't you absorb this MLM into them, or there is a normalization condition on these R and S?
Right. So ultimately, you would have to impose boundary conditions on the radial equation, and that would basically set the boundary conditions would set the normalization that you talk about. Yeah.
Okay. Thanks.
So no, so it makes your statement very unclear. So are you looking at the psi4 on the horizon at infinity? I mean, at infinity, this is the waveform. Okay, it has nothing to do with tidal. So what do you mean?
Right. So this is more explicit, as I'll discuss more explicit later. This is strictly computed for the in the near zone region. In fact, 2 slides later, I'll talk about that. Any other questions? Right. So this is just a representation of the radial tzkowski equation. I'm not going to go into details. Just want to leave an impression that this is a simple ODE. I think it's also fair to say that the tzkowski equation is often not written in this form. And by this form, I mean that it's organized in terms of the poles of the ODE. So the poles here are actually the outer and the inner horizon and infinity. So this is just like for all ODEs, it is convenient to organize the ODEs in terms of their poles, because ODEs are essentially governed, the nature of ODEs are essentially governed by the behavior as you approach of these singularities. And for our purposes, the important point is that once you've written the tzkowski equation in this manner, you'll find that this term here dominates as R approaches R plus, the outer horizon of the black hole. So because this term really dominates the ODE, the residual, the constant P pluses should really be held unexpanded if you want to fully capture the physics associated to the event horizon of the rotating black hole. So this P plus term here is sometimes known as the superradiance factor, and it is directly proportional to the sort of this co-rotating frame and versus inertial frames, or difference in the frequency that I told you earlier on for a Newtonian rotating body. Okay. So this is just a highlight that whatever perturbative expansion that you work on with these radial equations, you really want to keep P plus held fixed, such that you don't lose any physics associated to it. For example, if you do a perturbative expansion in omega, you still want to keep P plus unexpanded. So this omega should stay. The final slide I want to talk about for black hole perturbation theory is that one of the powers of the tzkowski equation is that the radial equation describes the behavior of the solution both near the outer horizon and at asymptotic infinity. So this is sort of related to what Damo was referring to, which is that so imagine I have a source located in this infinite radial interval. The tidal moments that I described early on is sort of valid in the so-called near zone region, where the which is basically the region between the location of the source and the event horizon, which makes sense because this sources the E's and the B's, and so the tidal field is sort of like exists only within this interval. But of course, the power of the tzkowski equation is that it also allows you to describe the solution at asymptotic infinity. And so what can ultimately perform a matched asymptotic expansion between the solutions in the near and the far region to compute the full radial solution in the entire space-time region. This is just to show you what the asymptotic behaviors of these radial solutions look like near the outer horizon. There's an ingoing plane wave component and outgoing plane wave component, and similarly in asymptotic infinity. And in order to impose the physical boundary condition of the event horizon, one would set this term to 0. And to impose the only outgoing boundary conditions at asymptotic infinity, one would set this term to 0. Just to say that hold this thought in this term, this scaling R minus R plus square, we'll come back again when I talk about the boundary conditions later. So hold that thought for a minute. So that was it for part 1. Any questions before I talk about the remaining parts of the talk? Excuse me. Okay, I hope it was clear. So in the next part of my talk, before I talk about the tidal response of curved black holes, I think it is actually instructive to first think about the tidal response of Schwarzschild spacetimes. And I'm careful in choosing my word spacetimes here, because of course it's well known that the Schwarzschild spacetime solution doesn't just apply to a Schwarzschild black hole, but it also applies to the exterior of a spherically symmetric relativistic star because of Birkhoff's theorem. Okay, and this is instructive because we know that the Luft numbers of general spherical stars actually non-vanishing. So by computing psi4 for these Schwarzschild spacetimes, we can actually explicitly see where the Luft number parameters first appears, and from that one can actually take the limit where the compactness goes to the size of 2m, the gravitational radius of the Schwarzschild black hole, and see how that Luft number vanishes. And once understands how that works, it's actually relatively easy to see how the tidal response of curved black holes vanish as well. Okay, if there's no questions, let me move on. So there have been heroic works in the past of computing the metric of a perturbed relativistic, I'm sorry, I can't pronounce this word, perturbed relativistic spherical star, albeit in the strict static limit where omega is 0. So in this case, there's no information about tidal dissipation, but at least there's all of the information about tidal deformability. For example, the time component of this metric component has this following form. This is just a Schwarzschild contribution, but there are also terms that depend on the external electric type tidal field, where analogously to the Newtonian potential showed early on, there's a growing term here, which only receives its contribution from the external tidal field. And then there's also a decaying term here, whose coefficient is exactly the Luft numbers. Of course, in GR, because of the presence of both the electric type and magnetic type tides, there are analogously both electric type and magnetic type Luft numbers. So for this time component, only the electric type Luft number appears, but one can show, we can refer you to these works that the magnetic type Luft numbers appear in the other metric components as well. So instead of looking at all of those 10 components of the metric, in order to make a direct connection with black hole perturbation theory, with psi4, it is instructive that we compute the Weyl tensor of this perturbed metric, project it onto a set of null tetras, and find the expression for its psi4. And if one does so, one finds that psi4 for the spherically symmetric star has the following form, which is exactly analogous to the tzkowski ansatz I showed you earlier on, where the constant here is just characterizes the tidal field sourced by external environment. And again, here we can compute this very explicitly, that the real part of this constant is proportional to the electric type tidal field, and the imaginary part is proportional to the magnetic type tidal field. As for the radial solution, just like the Newtonian potential showed earlier, there's a growing term here for the external tidal field, and there's also a decaying term here for the response of the body, where Ki now, I is just an index that labels both E and D, and they're contracted with this constant here. So the way that the Luft numbers of a general relativistic spherical star is computed by imposing the necessary boundary condition at the location of the surface of the star. So psi4 in this case has this simple form. So in general, well, in fact, for all stars that are not black holes, the radius is larger than 2m. And when we need to specify the conditions that we'll impose at the surface, and these conditions will allow you to uniquely determine the Luft numbers of these stars. Now, as for a Schwarzschild black hole, of course, the surface is located at 2m. Furthermore, as one approach the event horizon, you find that this growing term here actually scales as r minus 2m squared. And if you recall, this is exactly the radial behavior of this purely ingoing wave component that I showed you earlier on in the tzkowski equation. And one can find that this dl, this decaying radial term here, actually diverges logarithmically. And if one imposes the only ingoing boundary condition of the Schwarzschild event horizon, this term would have to vanish identically. And this is the classic proof that Love numbers of Schwarzschild black holes are zero. Of course, in previous works, it has been shown at the level of the metric here for ease of comparison and to make direct contact with black hole perturbation theory, just sort of show how this works in the case for psi4. Of course, one caveat of the expression above is that the metric was derived in the strict static limit when omega is 0, and therefore it does not contain information about dissipation. To derive the dissipative response of Schwarzschild black holes, one would have to relax this assumption. And for black holes, fortunately, we can do that relatively easily through the tzkowski equation, where one would do a perturbative expansion in this dimensionless frequency, m omega. And if one does so, you'll find that the radial solution, if you compare them, they just differ by a term here in the argument, where p plus tilde here is nothing but the spin zero limit of the superradiance factor that I discussed earlier on. And now if you repeat the same exercise and you expand the psi4 at large distances and read off the coefficient of this decaying term, you would obtain the tidal response of a Schwarzschild black hole, where at leading order, the real part of the response function is 0. This is just a classic result that the Love numbers of Schwarzschild black holes are 0. And on top of that, there's now an imaginary part here, which quantifies the tidal dissipation of the Schwarzschild black hole. So here in my paper, I have a general expression for this dissipation numbers for all values of L and M. And one can show that in the limit where L is 2 in the dominant term here, one restores some of the results that have been derived in earlier works, for example, in this work where they derive the L equals to 2 coefficient for this term. So this is a slide just to make clear and juxtapose the tidal response of a non-rotating body in Newtonian gravity and the Schwarzschild black hole, where you see that this tidal deformability parameter is 0, and the functional form here is exactly matches with the response, the dissipative response of the Schwarzschild black hole, where now the typical delay timescale is just given by 2m, which makes sense because this is the only timescale of the black hole, which is the light crossing time. Now, one interesting point I want to make here is that because for a Schwarzschild black hole, an external tidal field, there's really only one timescale set by the frequency of the external tidal field. And so in the limit where omega is set to 0, all of these terms, so these high order omega corrections here, would vanish identically as well. So some of the high order frequency terms have been computed in the recent work, and they all vanish when omega is set to 0. So
can I ask another question? Another naive question. May I? Am I too bold in expecting that this should be independent of M for Schwarzschild, or little m?
Little m. Yes, indeed, right. Because of spherical symmetry, indeed. So this is actually right. I'm writing here for full generality, but of course, because of spherical symmetry, it doesn't depend on little m. Yeah. This is just to say that when omega is set to 0 for strict static tie, the total response of a Schwarzschild black hole would be 0. But this is actually not the case for Kerr black hole, as I'll discuss right now. Any questions before I move on? Okay, now I'll talk about the tidal response of Kerr black holes. If you actually understand the two parts of this talk, it's actually relatively straightforward to derive the tidal response of the Kerr black hole because of the power of the tzkowski equation. So if you now derive psi4 for the curved black hole, you find that the near zone radial solution has this term here, where P plus is exactly the superradiance factor that I discussed earlier on. And it's easy to check that all of the calculations just restores the Schwarzschild limit when A is set to 0. Okay. And so the upshot is that you repeat the same exercise and you find that the response function for a curved black hole has the following form, where the real part of the tidal response is 0, and the imaginary part is obviously non-vanishing. So here, the conclusion, therefore, is that the static Luft numbers of the curved black hole vanishes identically, but because there's no approximations made on either the spins or in LNM, this result is true for all values of black hole spin, for both Schwarzschild up to extremal curved black holes, for all values of LNM in the multiple expansion of the external tidal field, and for both electric type and magnetic type tides that I denote by I here. I should, of course, acknowledge that some partial results of the tidal deformability of rotating black holes has been derived in the literature in these works, for instance, where they've derived the tidal deformability of a small spin black hole and for the dominant L equals to 2 perturbation. And in those cases, they found that the Luft numbers are 0. But this is a generalization of that result. Of course, I should also acknowledge that after my paper was put up on the archive, there are several groups who have independently confirmed that this is the case. For example, in this work by Goberger, Lee, and Rothstein, they took this 0 as an input to their Whirlline EFT calculation and were able to reproduce known results in the literature for the tidal dissipation, say the flux formula coming from tidal dissipation. And there's also a more recent work by these authors who have independently showed that this is 0 for a gravitational perturbation, but on top of that, also for a scalar and a massless spin 1 perturbation. Now, moving on to the dissipative part of the response, of course, as you would probably expect, this is proportional to the superradiance factor that I discussed earlier on. And this is actually a non-trivial generalization of the dissipative response of a Schwarzschild black hole for a few reasons. Firstly, this term here is very interesting because depending on the spin of the black hole, it can either be positive or negative. And the limit where this term here is negative, you just restore the normal intuition that energy and angular momentum are lost, will fall into the black hole. But on the other hand, when the spin of the black hole is large, this term can flip its sign, turn positive, and this is the case where you can spontaneously extract energy and angular momentum from the rotating black hole. And this is the phenomenon of black hole superradiance. This is a slide to, again, sort of directly compare the response function for the Schwarzschild and the curved black hole. And you see that this really is a non-trivial generalization, as I've shown you earlier on. And one of the most important non-trivial generalizations, which I've discussed in the case for a Newtonian rotating body, which is that now in the limit where omega is set to 0, tidal dissipation of a curved black hole is still non-vanishing because of frame dragging effect, right? This is, again, just to repeat the picture that now when the object, the black hole, is spinning, even in the presence of a strict static external tidal field, in the co-rotating frame of the curved black hole, the external tidal field would be perceived to be rotating at a frequency that's proportional to the spin of the black hole. And as a result, one can still experience tidal dissipation. And of course, this process, which we just keep going on and on until tidal locking happens, when the spins of the black hole and the external tidal field synchronizes, just like how Moon is locked to Earth. Okay, this is the slide that I've debated with myself and with colleagues for a long time as to whether I really want to talk about this, but I think that it's fair to say that there has been a growing interest and arguably confusion in the literature as to whether black holes have vanishing Luft numbers or not. And I get asked about this too often that I felt compelled to make a comment on it. So some in the audience may know that there have been claims put out into the archive last year in the summer by the same set of authors that spinning black holes fall in love. Okay, I think it's safe to say that when these papers came up, it generated a bit of controversy because the claims are actually in tension with some of the earlier results that I described here, and particularly in this work for the in the small spin limit and for the dominant L equals to 2 perturbation. And personally, I think that the confusion has been further hampered by the fact that this paper has been endorsed by PRL, which makes me feel a bit more compelled to make a comment on this. So if you look at the paper, and when they say that spinning black holes fall in love, what they really mean is that this term here is non-vanishing, and therefore black holes fall in love. And if you look at the first version of the archive, the initial claim is that this term corresponds exactly to the tidal deformability parameter of black holes. And so I believe that's why they call them, they have this title there. But of course, if you delve deeper into the detail in the paper, well, first of all, this is imaginary. Yeah, I think this was, to me, the first sign that something was not quite, I was a little skeptical because of this imaginary component, and I hope that's convinced you that there really is a clear distinction between the real and imaginary parts of the response function. And in fact, if you look at the superradiant, the tidal response term that I showed you earlier on, if you take the omega to 0 limit, and through some clever identities, you will find that this term exactly matches with what the authors have. Okay. So I hope it's clear, therefore, that one of the key messages of my paper, in fact, is that what these authors have computed is actually not tidal deformability, but instead these are actually purely dissipative effects. And this is actually, just to emphasize that, this has also been independently confirmed by other groups. Now, I think it's fair to say that after this has been pointed out by several of us, in version 2 of the paper and in the published version of the PRL and the PRD paper, they've effectively added a few sentences in the paragraphs and effectively redefine what they mean by love numbers. For example, they add the terms here that say that under the assumption that what they've computed gives rise to purely conservative effects, so on and so forth. All of this is just to say that what they mean by love in the title and in the abstract is actually the sum of both the conservative and dissipative effects, and not the original claim of the tidal deformability parameter. And I hope this is clear. I don't like to be put in this spot of saying that who's right or who's wrong, but I think that there's a lot of confusion in the literature, and I really feel that I should speak out on this. And I think it's fair to say that at least in the gravitational wave community, what we mean by love numbers is the tidal deformability parameter. And for example, we always say love numbers of neutron stars, and by that we always mean the 5PN conservative effect. So by this nomenclature, by this definition, the static love numbers are 0. But I think at the end of the day, regardless of how you define love numbers, regardless of nomenclatures, at the end of the day, to me, what's important is that what are the physical imprints? Well, to me, what's important is that these are two completely different physical phenomena, and they have completely different physical imprints in the phase of waveforms, right? So the tidal deformation parameter, just to emphasize, first appears at 5PN order. And in this case, for a rotating black hole, the coefficient would be 0. And for a tidal dissipation of a rotating black hole, this would first appear in the phase at 2.5PN order, and is proportional to the superradiance factor. So one nice thing that I like to think of in terms of the tidal dissipation of the rotating body is that it is actually well known that this effect here has a v to the cube, so power v to the 3 enhancement or suppression between the Kerr black hole and the Schwarzschild black hole. In particular, it is known that for a rotating black hole, this effect first appears at 2.5 pn order, whereas this effect first appears at 4 pn order for a Schwarzschild black hole. And one can actually understand this relative hierarchy in V cube simply from the superradiance factor. In particular, if you look at this omega here, just from Kepler's law, you see that this actually scales as V to the cube. So that in the limit where the frequency of the black hole is 0, there's a V to the cube suppression of this effect for a Schwarzschild black hole. So I think this is a very nice picture, at least for me, of understanding how these power countings work. How am I doing with time? Okay, I think I still have 10 minutes or so. Great. Is there a question? Okay. So as you can imagine, the love numbers literature, I think, is a little messy. For example, there are also claims that love numbers are ambiguous in GR. And essentially, the argument here is that because one can perform arbitrary radial coordinate transformations in GR, the coefficient of the decaying term, in which you read off the tidal response of any star, would be ambiguous, would be dependent on the choice of radial coordinates. So that was the essential argument of why love numbers of objects in GR are ambiguous. But as I argue in my paper, I didn't show this very explicitly, but as I argue in my paper, this is a red herring, because at the end of the day, the solution that we just described, as Damor has very kindly pointed out, is that it's valid in the near region, and one would have to perform a systematic match asymptotic expansion between this solution with the far region, such that one matches the tidal response that I described earlier on to physical observables at asymptotic infinity. In fact, this work, this match asymptotic expansion has been performed, maybe I should point out, in earlier works, but there was also a review, I believe this particular paper, a review of doing these types of match asymptotic expansions to high orders as well. And I argue that if one performs this expansion systematically, there will be no ambiguous meaning of what the love numbers would be. And in fact, more recently, these set of authors have performed an explicit matching between the near zone solution and the Wilsonian coefficients that appear in the worldline effective action, and find that in those cases, the love numbers of Kerr black holes vanish identically. Okay, so this is just to say that the vanishing of love numbers of Kerr black holes is unambiguously 0 in the static case. So this is a final slide. I'm not going to go into details because this is something that I've been learning very actively myself as well. But historically, there's been a mystery as to why the love numbers of black holes vanish, but only in d equals to 4. And this has been a mystery from a field theory perspective. The notion of some vanishing Wilsonian coefficient invokes the idea of some symmetry, a hidden one that's not explicit. So there has been this puzzle has been around for some time. And recently there has been a lot of progress in understanding what is the origin of this vanishing of love numbers only in d equals to 4. I'm not going to go into the details, but there are two independent groups, this and this group. They have argued that, and both of which, by the way, found different types of hidden symmetry that is associated to these vanishing love numbers. But I think it's very interesting to see whether one can unify these two symmetries and ultimately explaining this fine-tuning problem, if you like. So that's it. That's all I have to say. Thank you very much for, again, having me.
Thank you. Let's see if there are questions.
I have a question, Paolo.
Yes.
Speaking.
Go ahead.
Actually, I just want thank you for a clarifying talk. Just some comments. Are you aware of the fact concerning tidal dissipation of rotating black holes in an let's say, external static moon. Are you aware of the old work by Jim Hartle and myself, where one could compute using the Navier-Stokes equation and the viscosity of a black hole horizon, compute the dissipation effect?
Sorry, yeah, I apologize. I'm not aware of that
Okay.
work.
I'll send you just, it's not important. And by the way, I was the first one to say that the love number K2 of black holes is 0 in 1982, also on the way. But I wanted to mention, as you said, that there is no tidal deformation of black holes, that actually there are two love numbers. You know, there is the K2, which is the induced quadrupole moment, and H2, which is the induced deformation of the shape of the object. And some time ago, we computed that the second love number is not 0. I mean, the first love number, H2, is not 0, which means that the black hole horizon is deformed by external tidal fields, right? But it's a separate issue.
Yes, yes. Thanks for the clarification. Yeah.
Martin?
Yeah, thank you. Very nice talk. Can I ask a question just based on a simple experiment, if I understand the results? Suppose I have a static observer observing a curved black hole, and I measure the tidal fields at the location of that observer. Does or does not that tidal field depend on the mass of that observer?
Mass of the observer.
Yeah, so the observer would induce a tidal field on the black hole. Is or is not there any response in terms of the tidal fields that the static observer sees? I think that is what people classically would call a tidal response, just from a pure physics.
Sure.
And it still isn't clear to me whether the results that we have here, as far as I can see, there's a lot of discussion about how to interpret results. Everybody is pretty on agreement of what the actual mathematics of the perturbations is, just what to call them in some sense.
Right.
And is your statement that there would be no dependence on the local tidal field observed by this observer on its own mass?
So I can tell you from a mathematical perspective, well, first of all, locally, of course, the equivalence principle tells you that one cannot do so. But of course here, by working with the tzkowski equation, I really am strictly speaking working the linear perturbation limit. And you can think of it as being basically the tidal field sourced by a point particle, if you like, right? It's just a purely a small perturbation. Now, in that case, I don't think I have a clear answer to that because I guess at the end of the day, you're asking how do I measure these tidal responses. I would argue that gravitational waves would obviously be the way to go, but you're asking locally if I shoot a rocket, if I'm around, I'm in the vicinity, right?
Locally, you can measure a tidal field.
Right.
You just put something else that has a response to a tidal field and measure its deformation. That is a perfectly physically reasonable thing to measure. We can't measure other things, but we can always measure tidal fields.
So a partial answer, I'm not sure if that completely satisfies you, is that from the effective field theory point of view, which is exactly sort of trying to address that type of problem, right? So instead of doing a matching with radiation at infinity, gravitational waves, and that formalism, what you're matching is what the local observer would observe from the world line effective, from the local observer's perspective. And as I alluded to early on, there were earlier works that so these authors, they have computed that matching explicitly, to which these coefficients, these left number coefficients are 0. So I think that partially, I think that addresses your question, hopefully. In those cases, of course, for black hole,
in a sense, is the answer yes or no? Because I asked a yes or no question.
I think one can measure these tidal effects. this is what the EFT of the whirl line is about. And for a Schwarzschild black hole is 0. Sorry, for a curved black hole in the static limit, it is 0. So one cannot measure it because it's 0, but not that one cannot measure it. Does that make sense? Yeah.
Alessandra?
Yeah, I just want to make just a comment, related with this question that Martin posed. Now, independently on what can be measured of tidal effects in the waveform, I think as Chia has very well, clarified in this talk and in his paper, the confusion of the paper by Letierk and collaborators was that it gave the impression that there was some missing term related to tides that people had not identified before, and that for that reason, this lab number was different from 0. But at the end of the day, what they computed was basically this dissipation effect that was known since a long time, known to be 2.5 pn with spin and 4 pn non-spinning. So that was the confusion, that they were alluding to some new term that was missed and that was non-zero. I think this is what I understood at the end.
Yeah, indeed. And I hope that I've made clear that it is exactly a tidal dissipation by showing explicitly the superradiance factor here that naturally explains the hierarchy that you mentioned.
Sorry, can I make one comment? Can you hear me?
Sure. And your kid.
Yes. Yeah, that's why I'm not actively participating. Yeah. It was very clear that it couldn't be the static guy, right? Because the E square operator does not match into this. Actually, if you match the coefficient, it's exactly 0. And this at linear order in the spin, you didn't mention it, but I did this long time ago with the matching. And this is the linear response that Letierk and Casar were finding. So the generalization in Ira's and Walter's paper was to all order in spin, but was some result from 94 we could get from the whirl-line effective theory, and we knew it a long time ago. Right. Another thing which is interesting, which is the question for field theorists when you talk about fine tuning, is that the matching at the UV scale is 0. That's fine, but what is surprising is that there is no running, there is no logarithm, which is the real confusion, right? It's not just that the coefficient in the UV scale is 0, there are no logarithms, there is no physical log of R at 5 pn, which is part of the discussion. So you see this in the matching as well, there is no log for the E square, but there is a log for the E dot square, which is very interesting, that guy runs. So it's actually very unique of the static limit that there is no running for this coefficient.
Right. So as I alluded earlier, Poisson recently has computed these deformations at the level of omega square, and those are non-vanishing. He showed explicitly.
But
exactly
we knew that actually.
Square.
That's right. And we knew that because we saw the running of this coefficient already in the response. I mean, there's, as Alessandra said, there is nothing really new here. We almost knew everything. What is nice is that you can, anyway. But we
and also just comment that E square, of course, the confusion there is it assumes that there's no spin. So one can write many more operators when you have spins. And in those cases, it wasn't clear, at least my understanding from the field theory perspective, that those coefficients are 0.
No, that's right. But if you do the matching for the operator that they would have written for their response, you get 0. So it was clear that that could not be the static love number. Their operator matches into exactly 0 because symmetric times antisymmetric is 0. They could have realized this themselves. If they would have taken the lambda IJKL that they wrote and they dotted into EE, they would have gotten 0.
Right, it would be 0 because it's symmetric and antisymmetric.
Exactly, it's obviously 0. And I told this to Alex a million times. They published the paper anyway. It's not.
So one thing they'll say is that in their PRL paper, they do have a line, an equation of like some whirl line, some action that I wasn't sure it actually was relevant to. Anyway, just to say that, I think
well, the thing is they thought, because it's linear order in a spin, it has to be some generalized response function, this lambda IJKL. But if you actually go ahead and dot that against EIJ, EKL, you get identically 0 because this guy is symmetric, this guy is antisymmetric. So they never actually computed it. They thought, oh, it must be this. But if you actually put it on, you get 0. So this is obviously a dissipative effect. And as you said, And Aaron Walter did this all the spin case, but I did the linear spin case, and I don't see a reference here. And you know this paper very well. This matches Poisson result. And Poisson, when this came out, I told Eric precisely that. Eric, they just found your answer. And Eric realized this as well. And as Alessandra said, this is known, right? So which is fascinating.
Actually,
yeah.
Yeah, I'm not claiming, I mean, deformation and distribution, I'm not claiming that. In fact, these are, as you said, as everyone agrees that these are known results. I think my role here, first of all, is to clarify the
no, it was very nice. It was absolutely very nice, indeed, yes.
And to show that sort of generalizing this result, which can be seen clearly here.
But I think one of the most interesting part for the binary problem is that there is no logarithm. Because even if you found a 0 there, if there had been a log, we will need the log number in the two-body problem anyway.
Right.
So this is much more interesting that actually there is no log, which there is log in higher dimensions. So you actually do get running in higher dimensions. So that's actually physically much more interesting. But anyway, that's another question. Sorry.
Other question to this talk? Or?
Just for curiosity, I guess this no log number extends to charged black holes, although they are not very relevant.
So I think, yeah, so I have not computed this explicitly, but to be honest, I think it's from my experience working with the tzkowski equation. And if you have charged black holes, what will only change is that if you look at the radio equation here, there would just be sort of slightly more complicated terms here. You have charged superradiance in that case, so P plus will be a bit more complicated. But essentially, I mean,
it should go through.
I am almost 100% confident that in those cases, the response will be 0 as well.
Even the polarization is 0. You get all 0. Yeah, everything is 0. It's really amazing. Yeah.
Only
doesn't want to
4.
get any.
Of course.
No, obviously, all of this only flies in the equal 4.
Only in the equal 4.
Yes. No, actually, no. In other dimensions, in 5, I think it also you get 0 because you get this rod decomposition that allows you to factorize the perturbation similar to tzkowski. So I think 5 is also 0, but 6 you start getting not 0.
And is there a simple way to understand this new hidden symmetry?
It's a good question. I've been trying to digest that myself. From what I understand is that, so I've been reading a little bit more of the of this paper simply because it appeared earlier, so I had more time to digest. So what they found is that there's actually, it's miraculous. So I talked to Misha about this. By clever ansatz, he found a set of killing vectors that satisfy SL2R Lie algebra. And so this algebra, this killing vector is true for all D, okay, D equals 4, D equals 5, etc. But so the question is, why is it that only D equals 4, that left numbers are 0? And in their paper, they claim that it's related to the fact that in D equals 4, the representation of this Lie algebra is finite. So there's like a highest weight solution, only at D equals 4, and that highest weight solution gives rise to basically the solution for that, and that dimensions has no decaying terms, and in those cases left numbers are 0. But this is a very high level because I have not worked out the detailed calculations myself. It's something that I've been learning myself as well.
Yeah, there is a question by Justin.
Yes. Hi, thanks for the very nice talk. And at some point, I believe you mentioned a reference that you said did a matching calculation.
So
also,
high PN.
Right. But also connecting to, let's say, Wilson coefficients in a world line action.
Yes. So it's so this paper,
okay.
February. Yes.
Okay. And was that also with spin?
Yes.
Okay. Thanks.
It's with spin, and they generalize the vanishing response to scalar, to massless vector, and for massless tensor. So basically the tzkowski equation for arbitrary S.
Mm-hmm. And so
but nobody has calculated the cross section. The actual on-shell matching, I think, hasn't been done. so far.
Right. I think
So
that's
this
true.
is what everybody complains about, that we do the matching always solving the tzkowski equation rather than computing the cross-section. By computing the cross-section, you need omega to the 4 in the amplitude, which is really hard to control. So nobody has done that calculation yet.
Thanks.
I mean, I guess we can go to the discussion section. I don't know how to proceed.
In my opinion, there was no structured discussion session now, except if we want to continue yesterday's discussion, because we had to cut it off, to cut it short. So I don't know how Raphael feels, whether you want to come back to a few points or we
I don't know if we will
tomorrow.
come. Yeah, we will come back to this tomorrow. I don't know if how many people are around or whether people want to continue discussing this issue we started yesterday about the dictionary. I think Gregor is here. Maybe he prepared something. I need to watch my kid that doesn't kill himself. So,
as you prefer. I mean, we can leave it till tomorrow, but if Gregor has a few things to say, for instance.
Well, maybe. Okay, I actually, so there was something interesting yesterday that Donald mentioned. I'm not sure if he's here, but so one question I had is, because he proposed that we should compute amplitudes in a sort of word line setup. And I wondered if there's, there he is, yes. And I wondered, I mean, would this be really useful or not? Because somehow we don't quite understand if double copy works. We would have to work out all the unitarity, or, yeah, I mean, what would we gain doing that? Maybe that's my question.
Yeah, I guess you're asking me.
Exactly. For example, or someone, whoever has an answer to that.
Yeah, I mean, well, I think it could just be useful, at least for clarifying aspects of, I mean, some of these things that you mentioned. You know, I mean, I like to compute amplitudes. I think amplitudes are fantastic things. On the other hand, obviously, you know, if you want to apply scattering amplitudes to classical phenomena for point-like particles, then you want to match it as closely as you can to a word-line EFT, because that's the right EFT, right? So it's convenient in that regard if you can make them, you know, the word-line EFT speak a very similar language to the scattering amplitudes. Now, you can make expressions in the word-line EFT that look a lot like scattering amplitudes. I mean, of course, the Feynman diagram expansion of the word-line EFT is basically, the perturbative expansion of the word-line EFT, you know, the Feynman diagrams you draw, are a perturbative expansion of the equations of motion of the EFT. I mean, that's the sort of, that's the point of these things. So, and, you know, amplitudes, like the observables we're computing, you know, also, you know, obviously, you know, cook up solutions of the word-line EFT equations of motion. So they're closely connected, right? It's a little bit annoying when you're thinking about the word-line EFT to say, oh, okay, I'm not just looking at an amplitude. I have to make an observable. There can be some other factors. There can be, you know, this thing that happened. That thing, there can be something that cancels. And it would be nice if one could connect these things at line 0 without worrying about some cancellations or something. Yeah. So I think it would be clarifying. So for example, I mean, I guess I mentioned it yesterday in the context of the poles. You know, one can choose some organization of the poles that you're, you know, take a relativistic scattering amplitude anchored to, sorry, my sound is just about to fail here. Maybe I should fix that.
Can you still hear me?
Yes.
Yeah, sorry. It's a very interesting talk. So listen to more carefully. But yeah, so it was, you know, interesting, or it's clarifying to understand that. Okay, look, I mean, I got this relativistic amplitude. I want to compare it to the word-line EFT, maybe some poles. You know, I want to treat my propagators in some way. You know, keep these terms downstairs, expand those other terms in order to match it more directly. These are the kind of things we're thinking about. There are other examples. So another example somehow is this funny business about going to one of the reasons why I like to work in spacetimes with signature 2-2 sometimes is because there are on-shell quantities at 3-point amplitude level, like 3-point amplitudes that somehow are on shell. So you can compare, for example, the psi2 or psi4, I guess, generated by static objects in signature 2,2 spacetimes directly with scattering amplitudes. So that allows me to relate, whirl-line, basically, just a solution, a straightforward solution of whirl-line theory to a 3-point amplitude. And that's kind of a handy thing to do. But in order to do that, I have to compute the psi4. If I could just compute, some, but I mean, it's a 3-point vertex, so it looks a lot like you can match them directly. That's what I was getting.
I see. Yeah. Well, I mostly wondered if you would also, let's say, just implementation-wise gain something, if you could do things in a more clever way. I mean, well, I always wondered if you now compare what you do in QFT with a 4D scalar field somehow, would you really, can you somehow one-to-one map that to just like computing now the analogous amplitude in our whirl-line theory? And how similar would the computation? How much would you really learn from it? Because there were some papers that I started looking at where they really somewhat try to take this limit from a scalar field to a whirl-line, somewhat shrink it to 1D, and there's not much being followed up. But the limit seems to be sort of well defined. Yeah. So it seems to be possible, but I don't 100% understand it. So maybe that's my problem here.
Yeah, I don't know how to do it. I had to cover up these whirl-line type amplitudes. So, there are clearly objects which are very similar, and it would be nice if there was some machinery that allowed for a sort of straightforward direct comparison. I think it would help to understand some things. How useful it would be, obviously, I don't know.
Yeah, it might somehow be in between what we are doing now. Some missing a hole in between, indeed.
Maybe I can also say something. So it's probably also like what Donald said already. So for the spatial case of like waveform, if you compute this in field theory, say, okay, there's some 5-point amplitude, and of course in the whirl-line is clear, like you just compute the waveform. So in that case, you can sort of match these two, like the amplitude you compute in the classical limit is the waveform. But something funny is I don't know how to do this for like 2-to-2 scattering. For example, when we compute 2-to-2, we know the amplitude corresponds to the radial action or the impetus, depending on how we organize things. But in whirl-line, I have to commit to observables like impulse. Of course, I can plug in the impulse back to the radial action and compute the action, but it's sort of like stupid. It's not really the direct answer. So yeah, there's something I would like to understand too.
Yeah, I completely agree. We're trying things along this line that you don't need to go this way around. Indeed, I agree. Yeah, it's an interesting question.
So you mentioned the double copy equator. I think that is another thing which, somehow does seem to call for a very straightforward, link between sort of whirl-line quantities in electrodynamics and whirl-line quantities in geo.
Yeah, but there are some problems with whirl-line double copy. It's how much I understand. So
yeah, well, indeed. Yeah, but maybe it's a question of exactly how it's implemented. These issues where there are these, you have some delta functions and the tau parameters and so forth, and maybe one can sort of deal with that somehow. But no, I'm talking about some more quantum mechanical whirl-line object, more directly like an amplitude, where the double copy would work more directly. It wouldn't be so far away from just writing the sort of obvious vertices you see at the whirl line and just calling it an amplitude. Yeah, so maybe to demystify that slightly. We were able to see in with Ricardo Montero and my student Matteo, who's potentially here, and Ricardo's student David, about the this classical double copy thing in if you can analytically continue into a 2-2 signature spacetime, the classical double copy is super obvious. It's just the double copy of the scattering amplitudes, and it works just because the field strength object, the psi4 and the phi2, that you compute in these funny spacetimes, you can write them as integrals of momentum space. The kernel of the integral is the amplitude, so the amplitude double copies the relevant field strength quantities double copy, and that's exactly what Ricardo and I with Andres and Izzy call this Von double copy. So, but you kind of have to go through a bit of a machinery. You have to analytically continue into these funny signature spacetimes. So maybe you don't want to do that, right? It'd be fantastic if you don't have to do that somehow. You just say, oh, it's transparent, and got all Minkowski space with one time dimension, using some more direct method. But, I mean, I guess one way or another. I mean, it's sort of well, slightly irreducibly annoying that the 3-point amplitude doesn't really have any support in Minkowski space. Maybe there's no way to get around that.